All right, so as I said, we're going to continue on today in our treatment of nucleophilic acyl substitution reactions, which we've made clear go by a mechanism that's neither SN1 nor SN2. It's really its own animal. And in particular today, we're going to look at the reactivity of acid chlorides, acid halides, if you will, which are pretty much always going to be acid chlorides, and acid anhydrides, which have very similar reactivity. I'd have to give the slight edge to acid chlorides over acid anhydrides in terms of reactivity, but acid anhydrides, I would say, are in practice 90 to 95% as reactive as acid chlorides. They're very similar, but I think we're on pretty solid ground saying that acid halides are the most reactive acyl derivative. And then you can see who's joined us over here. You want to give this next part of the lecture? Can you tell them about acid chlorides? It's just hydrolysis. Nah, she doesn't seem real interested. Okay, so what I'd like to start with is in the same vein as what we did back in chapter 19, where we talked about hydration of aldehydes and ketones. And there we said, not only is this not a synthetically useful reaction, but it's the exact opposite of synthetically useful, right? Because normally water adding to acids and, to aldehydes and ketones is something we take steps to prevent from happening because we want to be able to use our aldehyde or our ketone, and we can't do that if water is added. So in a similar vein, hydrolysis of acid chlorides is the exact opposite of useful. But it's sort of something that is inevitable, that we're kind of cursed with. Any bottle of any acid chloride over time will hydrolyze because there's water vapor in the air. And so it can't be prevented. But by looking at the mechanism of this process in acidic solution and an alkaline solution, it's illustrative of those two types of processes. Just like in chapter 19, we looked at hydration of aldehydes and ketones in both acidic and alkaline solution, just to get us used to thinking about how mechanisms look under those two sets of circumstances. So same thing here. So what I've done over here is I've taken propanoyl chloride or propionyl chloride, you can call it either. That's the acid chloride of propanoic acid or propionic acid. And of course, if one were to treat this with aqueous acid, you would get propionic acid as the product. So we're looking first at what this mechanism would look like under acidic conditions. And by the way, all you would really need to do for this reaction to start happening is take your bottle of propionyl chloride and open it. You know, expose it to air. There's going to be water in the air, water vapor. There will always be a little bit of acid in any sample of acid chloride. You'll always have a little bit of HCl. It's impossible to prevent that from happening. There's always going to be a trace of that. And so little by little, you will convert the acid chloride to the carboxylic acid, which by the way is counterproductive, right? Because we've already said carboxylic acids are the least reactive acyl derivative, and acid chlorides are the most reactive ones. So you basically just ruined your acid chloride. But that's just part of what we have to deal with when we're working with acid chlorides. They are very reactive, and even just opening the bottle and exposing it to the water vapor and air is going to be a problem. So what would this mechanism look like in the presence of aqueous acid? Well, here we need to be sure that we don't use any strongly basic anions. So no alkoxide ions, no OH minus, nothing like that. Those species do not make sense under acidic conditions. When we look at what we're given, all we see is H3O plus. And yes, sometimes Al will put H3O plus, comma, H2O. I'm not a fan of that because to me that's redundant. H3O plus implies that water is present. You can't have hydronium ions without water. And that's really what we mean when we talk about a dilute aqueous acid solution. It means that you've got some H3O plus ions dissolved in water, right? Because you can't have just H plus ions floating around. There's no such thing. So the first step, as we've seen so many times before in aqueous acid solutions, is we're going to protonate that carbonyl oxygen. And we're going to use the only species that makes sense with what we're given, which is a hydronium ion. So we'll use that to put a proton on our carbonyl oxygen. Now this species is ready for nucleophilic attack. And so our nucleophile will in this case be water. That's the only reasonably nucleophilic species that's present. And so water will attack the carbonyl carbon, and we'll get the addition product, or the product of the immediate addition of the water. Yeah, I think that's all we really need to say about that. So that intermediate will look like this. This is our tetrahedral intermediate. Now we need to pull off a proton from that oxygen so as to be able to get to a neutral intermediate, an uncharged intermediate. That's going to be necessary for us to be able to lose this chloride ion as a leaving group. If we don't pull that proton off, then we'll wind up with a species with a +2 charge, and that's no good. We want to avoid that at all, if at all possible. And so many of these questions, why do we have to do that step first? Well, draw the step out without doing that first and see what you get. And I think in general, you'll find why the order of these steps makes the most sense. With any mechanisms, of course, the mechanism doesn't imply that every single last one of those molecules does exactly this. It's simply saying that the vast majority of them do. And there might be some other minor pathways. It might be that, every 1 in a million molecules gets you the species with the +2 charged intermediate. But overwhelmingly more common than that is for the reaction to go through this mechanism, I think. One thing I actually do want to add one thing to this step back here. You'll notice that, of course, we're not using a hydroxide ion. That does not make sense in acidic solution. There might be 1 OH minus ion for every 10 to the 20th water molecules and H3O plus ions. If present, it's in such a minuscule amount that it doesn't make sense to use it in a mechanism. So that's why we're using water as our nucleophile. In alkaline solution, to use OH minus as a nucleophile, we're perfectly good. That's perfectly reasonable. Not an acidic solution. In any case, after pulling off this proton with a water molecule, we get this intermediate, and now we can lose our chloride ion. And of course, it doesn't matter which of the two OH groups we use to do that, they're the same. And then we have our carboxylic acid, essentially, except that it's protonated in the oxygen. And all we would need to do is invoke a water molecule, again, not OH minus. That doesn't make sense in acidic solution. But we use a water molecule to pull that proton off, and we get our free carboxylic acid as the product. So that's how that mechanism would look in acidic solution. Let me, so to speak, back off the camera a little bit so we can fit for a moment at least all of those steps on one screen. So that I think is the most reasonable way of drawing that mechanism in acidic solution. But this one can also happen in alkaline solution. And again, the reason we're going over these hydrolysis reactions is not because one would ever do either of these steps in real life. Not that at least I couldn't imagine, but it's to get us used to the idea of how it is that acid chlorides will behave under either acidic or alkaline conditions, so that we're ready for either type of scenario. In general, what I think you'll find is the more reactive the acyl intermediate is, which again, acid chlorides are pretty much as reactive as they get, the likelier you'll find that it will react under either acidic or alkaline conditions. As the intermediate gets less and less reactive, then you might find that it will only react under acidic conditions or under alkaline conditions. And we'll cover that as we go on. We're going to take this very stepwise, but I think we'll find that it makes sense that there's always a good reason why this reaction can only occur in acid, let's say, but that reaction over here will work under either acid or alkaline conditions. Good, so we'll get to how the mechanism looks under alkaline conditions in just a moment, but I want to make sure first that there's no questions on that mechanism here, everything kind of making sense. Hoping that by now everything's starting to look like same old, same old. I don't think there's any steps here that are completely different from ones we've seen, but I just wanted to make sure that's clear. That being said, and I think I've made this point before, as we get closer and closer to the end of the semester, I'm going to become less and less able to surprise you. That it's going to get to the point that everything I show you is like something we've done before. So that's how the mechanism would look under acidic conditions. What about alkaline conditions? Well, I believe I've made the point that under alkaline conditions, as compared to acidic conditions, in those cases like these where we have a reaction that can go either way, I think you'll find that under alkaline conditions, it's more straightforward, more direct. There's fewer proton transfer steps. That being said, there is going to be a bit of a hitch, but it's not an unexpected hitch. It's something that, it too is something we've seen happen before plenty. And once again, I'm just using this particular acid chloride as an example. I could have picked any acid chloride. But since we're under alkaline conditions, we're going to treat this with aqueous hydroxide, and that could be sodium hydroxide or potassium hydroxide, of course. The alkali metal ion is not going to participate in the mechanism. There's no way you can draw arrows that include there's no way you can draw arrows that include transition metal ions. But we'll start out by treating the acid chloride with aqueous hydroxide, and then we're going to find we need to do an acidic workup because we'll wind up not with the free acid, but with its conjugate base, with the carboxylate ion. And so we need to acidify in order to put that proton back. But we've seen that kind of thing before. Since we're under alkaline conditions, now we don't have to worry about protonating that carbonyl oxygen first. In fact, we'd better not, because if we were to do so, we'd have a cation under alkaline conditions, and that doesn't make sense to generate species that look like that under alkaline conditions. They're too reactive. They would be either immediately deprotonated or would immediately suffer nucleophilic attack. So as is so often the case in alkaline conditions, I find they're more straightforward. It's just bombs away. Our nucleophile attacks our carbonyl carbon. And of course, it makes sense to use hydroxide here since we're given it. We know that it's present. So that's going to be by far the most alkaline species present. And we're going to go as far as we can under alkaline conditions until no further reaction can happen. Remember, that's what the numbered steps means. It means we add the aqueous base and we wait until everything has reacted as much as it can, and then we acidify. So that's what that means here. So hydroxide ion attacks, we get this intermediate. Now we don't have to worry about any proton transfers. This tetrahedral intermediate can just collapse and kick out the chloride. But remember, you do have to form that tetrahedral intermediate. You need to form the intermediate that has that sp3 hybridized carbon. Again, this mechanism is neither SN1 nor SN2. It's something different from both. It's its own kind of reaction. So once that's done, once we kick out the chloride ion as the leaving group, we generate the carboxylic acid. And so you think, well, I'm done. That's my product. Careful, not so much. We're not done because we've just generated an acidic species and we're still in the presence of alkali. Remember, we keep reacting until nothing further can happen. under that set of reagents. And then we do the second step. And the way you know that this deprotonation is possible is by pKa's. You know, the pKa of pretty much any carboxylic acid. I don't know what it exactly is for propionic acid, but I bet if you looked it up, it would be round and about 5. And so if we're here at, say, pH 14 in a solution of aqueous hydroxide, we're well above the pKa of the carboxylic acid. And so there's no way you can prevent that deprotonation from happening once you generate that acidic molecule in the presence of base. So you can't prevent it. So you need to show that in the mechanism. You know, there's no way that you could sort of call down to all the little molecules in the flask. Excuse me, would all y'all mind not getting deprotonated by the hydroxide? Because if you do, then I have to write more things in the exam. They don't care. Molecules are quite heartless. They don't care about your feelings. And so that's inevitable. You can't stop that from happening. And then once that deprotonation occurs, now what you've got swimming around very happily in your alkaline solution is this carboxylate ion. And that now is fine. That will keep on swimming around in the alkaline solution until we add aqueous acid. That's when we acidify. The first action of the aqueous acid is going to be to neutralize any leftover base. And of course, that's just a straightforward inorganic reaction. You drew that sort of thing 5 billion times when you were in Gen Chem. It's just H3O plus OH minus yields 2H2O. And then once all of the hydroxide ion is neutralized, then the acid will start protonating that carboxylate ion. And of course, that mechanism is by now quite familiar to us, I hope. We use a proton from hydronium to put a proton back onto the negatively charged oxygen, and then we've got our free carboxylic acid. And so that's how it is that we generate that. So let me back off again the camera so that everything fits on there. These are different things. We'll get to those guys later. But that's how the mechanism would look in alkaline solution. And again, I think if we're fair-minded about this, we'll find that once again, the mechanism in alkaline solution has fewer steps than the corresponding mechanism under acidic conditions. And I think you'll find that's always going to be the case. At least I have yet to find a counterexample. Whether it's 1 step fewer, 2 steps fewer, that might vary. But I think in general, you will find if you look at the situation and are open-minded and fair-minded about it, I think in general, you'll find for those reactions that can occur under either set of conditions, the mechanism under alkaline conditions should have fewer steps. Now, not all types of reactions can occur under both sets of circumstances. We've already covered, for instance, Fischer esterification. That was in the last class, where we said that that can only occur under acidic conditions, will not occur under alkaline conditions. And I don't want you just memorizing that sentence. We went over that idea, and I expect you guys to understand why we covered that here in class and in your class notes. The reason that you can't do an esterification under alkaline conditions is your base will just deprotonate your carboxylic acid and then you're done. There's no way you can esterify this. There's no way a nucleophile can add to that carbonyl. It's a species that already has a minus charge. So there is good reason for that. So the way you remember what can and cannot happen under which set of conditions is by understanding the relative reactivity of the species. It's not arbitrary. There's always a good reason for it. Good, so I think that's all we really need to say about that in terms of this hydrolysis business. Any questions in either of those mechanisms? Hydrolysis of an acid chloride. Again, useless as the day is long, but it's helpful for us to go over this, to get us used to thinking about how these things behave with aqueous acid around and with base around. Good, so everyone comfortable with both of those mechanisms. Wake up. You can't be asleep at 12:25 in the afternoon. Even though we're used to this being 11:25, I don't think there's a significant difference. Well, good. Oh, that's unusual. Bella has left us. Barnaby's over here on the floor. I'll let you see him later. We'll do the cat content during our reef session, which, by the way, we're just doing attendance today. So please register your attendance. That will be all 100 of the 100 daily points. But I do have a little problem for you guys to work on later that I think is going to be helpful. Good. Well, we know that acid halides will react with water, although we usually don't want anything like that to happen. What if instead of water, we substituted in an alcohol? So let's say we took benzoyl chloride, and again, we could take any acid chloride we liked. The same thing would happen. And let's say we dissolved it up in ethanol with a little bit of an acid catalyst. You might not even really need to add acid because, again, with any acid chloride around, there's gonna be some HCl around. I mean, if you wanted to press the point, you could add a drop of sulfuric acid or HCl. But either way, you're going to have ethanol with a catalytic amount of acid. And again, notice that we're not given water. So we can't use H2O and we can't use H3O+. We need to make sure in our mechanism that we use only species that make sense, given what's in the solution. But I think we'll find at the end we'll get an ester, in this case, the ethyl ester. So this is another way of making esters. We already learned about Fischer esterification. We also learned that you can take a carboxylate ion that you would get in principle from deprotonating a carboxylic acid and treat that with an alkyl halide, preferably primary, and it will undergo an SN2 reaction. So that's chapter 11 stuff. So that's a second way of making esters. This is yet a third. You can alcoholize an acid chloride or anhydride, in fact. Again, acid chlorides and acid anhydrides are pretty similar in reactivity, very, very close. I do believe acid chlorides, other things being equal, are going to be a little bit more reactive, but not by a whole lot. Still, we got to give acid chlorides the edge. So we've got ethanol present, and I could have, of course, chosen any alcohol, but we've got ethanol present and we've got a catalytic amount of base. That means the only other species present will be catalytic amount of acid. And so that means the only other species present is going to be the conjugate acid of the alcohol. What we will certainly not have any of is the conjugate base of the alcohol. The way you know that is by observing that we're under acidic conditions. So ethoxide ion certainly is a thing, it certainly exists. But remember, ethanol is a very weak acid. Ethanol probably is a pKa round and about 17 or 18. And we're under acidic conditions. So our pH is maybe 1 or 2 or maybe at most 3. We are easily 15, 16 pKa units away from being able to justify having any amount of ETO minus in this solution. Remember, we said the other day, general rule of thumb is you're okay if you're within maybe 7 or 8 pKa units. That's a good general rule to remember. We're way outside that here. So we know we can't invoke any alkoxide ions, not in this mechanism. So it also means that we, of course, need to protonate our carbonyl oxygen first, as is going to be generally the case under acidic conditions. We've seen this happen time and again. So how do we know what to put here to use to put the proton on? Well, we look at what we're given. And again, we only have the alcohol besides the organic compound. We have the alcohol solvent and a catalytic amount of acid that will immediately form the conjugate acid of the solvent. And the solvent's not water here, it's an alcohol. So that means we need to use the conjugate acid of the solvent in order to put that proton onto that carbonyl oxygen. Having done that, now our alcohol molecule can act as a nucleophile. And again, not ETO minus. That species does not make sense in alkaline solution. So I expect you guys to know that alcohols are not strong acids. And especially under acidic conditions, you're not going to have any of the alkoxide ion. So it's the alcohol that adds here. And we've seen this happening a bunch of times already, something like this. This is the point typically in acidic conditions where we'll look to see if we need to do any proton transfers. We do, because if we don't, then after the next step, we'll get an intermediate with a +2 charge. And that doesn't make a lot of sense. So we'll use, again, an alcohol molecule, not water, not ETO minus. You have to use species that make sense according to what you're given. Can you remove the, oh, is it still in your way? I had tried to, I don't want to do the update now because I'm worried it'll try to restart or something. So is this out of your way now? It is, oh, good, okay. So ethanol attacks, we get this tetrahedral intermediate. And now again, we need to remove that proton before we can go on. We need to use a molecule of the solvent that we're given in order to do that. If you were given a different alcohol, you would use that. This might not be ethanol. It could be any alcohol. So you'll look and see what you're given. You don't memorize ETOH goes here. That's not how to learn this material. It's always situational. You got to look at what you're given. Having done that, now we have this neutral intermediate, and we can use an electron pair on the OH group to kick out the chloride ion, and you get this intermediate. It's essentially the ester that we expect to get, except protonated. What do we use to remove the proton? Again, looking back at what we're given, the only species that's at all basic is the alcohol solvent that we're given. So we'll use that to pull off a proton, and we wind up with, in this case, ethyl benzoate. So that's how the mechanism would look under acidic conditions, which, by the way, I believe if you go back and look at the reaction with water under acidic conditions and compare that to this, I think you'll find the only difference is you're replacing water with the alcohol and H3O plus with the conjugate acid of whatever the alcohol is. So, so do go back and make that comparison. By understanding these types of comparisons, by making the comparison and looking until you can see that these are essentially the same thing, that will help you to know what you need to know for exams. To be able to see these are not different reactions, they're the same thing. They're both nucleophilic acyl substitutions under acidic conditions. That's going to save you a lot of trouble because that means when you come across a situation that you've never seen before, you will understand all of these correspondences and similarities well enough that it won't trip you up. Memorizing exact particular cases is not the way to learn the material. Good. So I think that's all I can think of to say about that. Now, what if we did do this under alkaline conditions? What if instead of aqueous hydroxide, we added ethanol and a little bit of ethoxide in the form of probably sodium ethoxide? You would still get the ethyl ester. That would be worth your trouble, is figuring out what the mechanism would look like under alkaline conditions. So instead of ethanol and H+, you had ethanol and ETO minus, or NaOET, or something like that. That I think would be worth your time. That would not be a waste of your time. And as always, if you work that out and you're not sure you did it right and you want to show me your work, please don't hesitate. That's what I'm here for. But I think you'll get a lot more out of it if you do it yourself without my holding your hand every step of the way. You can certainly use this type of mechanism here with hydroxide and water to help you out. And I think you'll find it's quite analogous to the reaction with aqueous base. Good. Where are we at? 12:35. We have another 15 minutes. That should be good. Good. Questions on alcoholysis of esters? Not of acid chlorides, not hydrolysis, but alcoholysis. Loosening, that lysis suffix means loosening, So hydrolysis is loosening with water. You're loosening carbon, you're loosening bonds. So this is alcoholysis, since we're loosening bonds using alcohols. Well, can you do the same thing with amines? Can you do an aminolysis of an acid chloride? And I should mention aminolysis, the spelling on top is the one I've always used. Your book uses this other spelling. Both are correct. Lysis was to break apart, right, or loosen. Yep. I believe that comes from the Greek, something like that. Good. So my knowledge of Greek is, minuscule. But generally, whenever we have borrowed words, they tend to come from either Greek or Latin. I don't think you'll find too many Y's in Latin. Good. So, but both spellings are right. I don't really care which you use. So let me do this so that stupid Dell update thing isn't in the way. And you'll be proud of me. My replacement computer is not a Dell, since I'm at least momentarily, at the moment, mad at Dell. This is it's a laptop by Asus, so it's a little larger and more powerful than this laptop that I'm speaking to you from. So this laptop can handle streaming, can handle most games, but this one here is more than good enough just for using Zoom, just for surfing the web or like that. Good. So let's consider how this would look if instead of an alcohol, we used an amine as the solvent. And this does need to be either a primary or secondary amine. Tertiary amines will not react irreversibly. The amine can add to the carbonyl, give or take a protonation, but after that, nothing further can happen. So it just falls back off. So you do need at least one hydrogen on that nitrogen in order to get an irreversible reaction. So here I'm using pyrrolidine as an example, and I know that I really care if you know this compound is called pyrrolidine, but I've learned by experience that I might as well tell you what these small molecules are named, because lots of people are curious, and I certainly love curiosity. I'll just also mention for the curious, the reason this molecule is called pyrrolidine is because it's a derivative of pyrrole, which looks like this. So pyrrole is a 5-membered nitrogen-containing heterocycle that's aromatic. Again, if you go back and review your chapter 15 stuff, you ought to be able to convince yourself that the lone pair of electrons on the nitrogen now is involved in the pi system. So our nitrogen atom is sp2 hybridized. That lone pair of electrons goes into the unhybridized p orbital, and you have 6 pi electrons. So that's pyrrole. Again, I don't really care if you memorize these names, but that does have a name, and pyrrolidine is just the reduced form of pyrrole. So again, I'm just explaining for those who are curious where these names come from. Let me get things out of the way of that Dell update thing. Good, but other than that, I think you'll find that everything that we said about the reaction of an acid chloride in the presence of an alcohol with an acid catalyst is exactly the same in the presence of a primary or secondary amine with an acid catalyst. And here I'm just using acetyl chloride as an example. You can pick whatever acid chloride you like, and probably you should do that when you're practicing. So first we protonate that oxygen, and the way to know what to use as the proton source is by looking at what you're given. You want to use, under acidic conditions, you want to use the conjugate acid of your solvent. And in this case, the solvent is essentially our pyrrolidine. So we'll use the conjugate acid. We'll use what we get when you add a proton to pyrrolidine. Because when you add a touch of acid, maybe a little bit of HCl, maybe a little bit of sulfuric acid, that will immediately react quantitatively with the amine. Of course, it will only protonate a few of the molecules of the amine. The vast majority of them will remain unprotonated. And that proton will, if you really want to get into the nitty-gritty, will now get shuttled around between different molecules of the amine. But there always will be a few molecules that are protonated, and most of them will not be. But it's one of those protonated molecules that will put the proton onto the oxygen for us. And then instead of the alcohol attacking, the amine will attack. And of course, you don't get to use the conjugate base of pyrrolidine. That's an exceedingly strong base. pyrrolidine is even less, or primary and secondary amines in general are going to be far less acidic even than alcohols, right? Alcohols are going to be pKa, aliphatic alcohols. We're not talking phenols, but aliphatic alcohols should have pKa's round and about in the high teens. I don't know the pK of pyrrolidine off the top of my head, but I'm confident if you looked it up, you'd find it to be well up in the high 30s, maybe even 40. So there's no way we can use the N- species. So that's how you know these things. You have to have a general understanding of the structures of these molecules and at least roughly speaking, the reactivity. So this should not be just a five-cornered box with an N in it. It should mean something to you. Having done that addition, now we again need to deprotonate in order to be able to do the next step. The only reasonable base to use is our solvent. And so that's what we'll use to pull that proton off, and we now have our neutral intermediate. Now we can use an electron pair off the OH group, off that oxygen, in order to kick out the chloride. And you say, well, can't we use the lone pair on nitrogen? Sure you can. You'll just get another resonance form of this intermediate. But there's, I can think of at least two more resonance forms for that intermediate. There's also the resonance form that has two single bonds and then a plus charge in carbon. And you can also use the lone pair on nitrogen and have a double bond. So all three of those structures contribute to the overall structure. And it's always possible to draw a correct mechanism using any of the resonance contributors. But you can certainly do it this way as well. Once you've got that, then it's essentially our product just protonated. And so once again, we'll use whatever the solvent is that we're given to act as our proton, our proton acceptor, our base. We put those electrons back on the oxygen, and we get our neutral amide molecule. So aminolysis of acid chlorides also works. Also of acid anhydrides. Just also in terms of reminding us of the reactivity of acid chlorides, you certainly can reduce them to primary alcohols using LAH, just like you can reduce carboxylic acids to primary alcohols. I've never heard of that being done. I've never done it myself. I don't know why I would bother making an acid chloride just in order to kill it off with LAH, because probably I made the acid chloride from the carboxylic acid, which I could just react with LAH directly. So I don't know why that would be done in real life, but if you did, it would work. LAH would surely reduce an acid chloride all the way down to the corresponding primary alcohol. And then there's some other reactions relevant to acid chlorides back in chapter 10. So we've already covered that last semester. You might want to review those. Other than that, that's basically it. Well, that and acid anhydrides, which we'll cover in a moment. We can start on esters on Wednesday. That's fine. There's no need for us to consider those today. We have time. What are we going to say about acid anhydrides other than that their reactivity is very similar to that of acid chlorides? Well, this is one of those times where I'm going to leave it to you. And I have a little problem for you guys to work on your own. So let me move everything around so you have a good chance of being able to see anything. So your mission today, should you choose to accept it, which by being in this class, you've already tacitly chosen to accept it. Oh crap, I can't, what if I do view details? Oh, good. Here we go. That will allow us to get that out of the way, and I can then update when class is over. Good. So the reaction you see here is making aspirin, and you might even have done this in either a Gen Chem lab or maybe even high school lab. But you start with salicylic acid, which has this structure. Salicylic acid is essentially benzoic acid with an OH group ortho the carboxylic acid group. And that stuff you can isolate it from willow tree bark. It's actually been used for thousands of years. Salicylic acid in itself is an analgesic, but it's not so nice on the stomach. Phenols are quite acidic, as are the carboxylic acids. So of course we temper that somewhat by acetylating the OH group. And you can surely use acetyl chloride to do that. It'll definitely work. But if I were given a choice in real life, I would rather use acetic anhydride than acetyl chloride. Acetic anhydride is also nasty, but probably at least 10% less nasty than acetyl chloride. And you can assume there's going to be acid around, just like with acid chlorides, there's going to be a little acid present. Or, you know, you can certainly add a drop of HCl or sulfuric acid to just press the point home. In any case, if you treated salicylic acid with acetic anhydride, you would get aspirin, acetyl salicylic acid. So that's your goal. What do we have now? We have 12:46. I'll let you think about that for 2 or 3 more minutes. Probably have already gotten started. Then I'll call you all back together. I do have the answer included in this PowerPoint file. And by the way, I've already uploaded this PowerPoint file to eCampus. So if you really wanted to, you could download it right now and look at the answer. But it's up there for you to look at in future. But that's what I would like you guys to work on for now. You can assume that some of the conjugate acid of the anhydride is going to be present. There's also going to be a little bit of the acetate ion floating around. And we'll talk about why that is. Acetate ion, of course, has a minus charge. So why is it that we can use that? So I'll let you think about that for another minute or two. Oh no, you have to see this. So Barnaby's over there kind of lying on his back or stretched out like that. I think he needs attention. I think we need to pick him up. Hi. Everyone wants to see you and admire you. Lying on your back like that. What a silly kid. They want to admire you. Okay. I don't think he wants to be, limited in his movements right now. He wants to check things out. Or maybe he just wants to be in my lap. He's a very sweet kitty, purring like crazy. Everyone wants to admire you. You're a cat, so you like being admired. You deserve being admired. See 1248. Would Barnaby. Okay, well, I'll just show you. This is how I did it. I won't say that this is the only correct way to draw this mechanism, but I think it's a reasonable way to do it. We need to start in any case by protonating wait, what's going on here? Again, I think we can just assume that some of that protonated compound is going to be around. Few molecules of it anyway. So our phenol can add now to that carbonyl, just like it would if this were a chlorine instead of another acetate group. Our alcohol can add. And then we need some proton transfers. And for this, it's reasonable. I was just going to get to why it's reasonable to have an acetate ion. The reason is this is not a terribly alkaline species, right? There's a big difference between a carboxylate ion and an alkoxide ion. because of the difference in acidities of their conjugate acids. So this is going to be the conjugate base of acetic acid. Acetic acid is a pK round and about 5. If we're here around pH 1, we're within, or pH 2, we're within 3 or 4 pKa units. That's fine. We can rationalize that. Whereas using an alkoxide ion, that's no good, because now we're not 3 or 4 pKa units away. We're more like 16, 17, 18 pKa units away. That's much too far. So I think you will find some carboxylate ions around. You can use that. If you're not comfortable with that, you could also use a molecule of acetic anhydride, right? Because after all, how else do we get some of the protonated acetic anhydride except by using an acetic anhydride molecule? So now, why are we using acetic acid and not, or acetate ion, not acetic acid? I don't think you're going to be able to protonate acetic acid because it's already an acidic species. So since we have some acetate ion around, there always is in the presence of acetic acid. So I think it's much better to use that. Or as I said, if you want to use the unprotonated acetic anhydride to pull the proton off and make the protonated one, that's perfectly reasonable, I think, in this case. I'm sure that both of those happen in real life. Once we've pulled that proton off, now we're ready to expel an acetate ion. By the way, that's another reason why we can expect there to be some of the acetate ion around. And again, I think the acetate ion is a low basicity enough species that we can rationalize that under acidic conditions. Again, the way you know that is by the difference in pKa's. If we're under acidic conditions, so again, round and about pH 1 or 2, and the conjugate acid of the acetate ion, which is acetic acid, has a pK around 5, I think we're well justified in using that species. CH3O minus, no way. There's no justification for that, not in acidic medium. But you can use an acetate ion to pull that proton off, or again, if you wanted to use another acetic anhydride molecule, I'm pretty confident that both happen. Once you do that, you've got your acetate ester, and that's aspirin. So this is, as I said, already on eCampus, so you don't have to worry about that. Other than that, I'm seeing 12:52 on this clock over here, so I'm out of time. So we'll pick up there on Wednesday, and I will see you all then. Have a good day.